Hello, Dr. Ko. In this video, I'll be doing my submission for exam 3. In this video, I'll be doing part 1. In this exam, we are examining a 50-meter long insulated bar that is perfectly insulated, and we're given its thermal diffusivity of 1 meter squared per second. We're told that it has an initial uniform temperature of 20 degrees Celsius throughout the bar, but suddenly the temperature at the left side of the bar is increased to 50 degrees Celsius, while all other sides remain perfectly insulated. And so in part 1 of this video, of this submission, I will be writing down a set of Crank-Nicolson finite difference equations, and from there we will go to part 2, where we will write code, solve and plot the temperature profile. But in this case, we are just writing down the Crank-Nicolson finite difference equations. And so, first off, we can start off by drawing the bar. And we know that it's perfectly insulated. And we know it's initially 20 degrees Celsius throughout. But then suddenly the left side, we can call this the left boundary, at Tx equals 0, the position 0, we can call that 50 degrees Celsius. That is the temperature it suddenly jumped to. But all other sides are perfectly insulated, and at this exact moment, the rest of the bar was still 20 degrees Celsius throughout. And so from there to here, that's all 20 degrees Celsius at Tx equals 50 meters. Okay, and so we want to analyze the temperature of the bar over time and throughout the bar. And the way we're going to analyze it is just by splitting up the bar into 50 different segments of position, and each position segment, delta x, will be 1 meter long, and so 50 segments for the entire length of the bar. And we'll also split up time intervals since we're examining the temperature of the bar over time and throughout the bar. And we'll do time segments delta t of 1 second for 1 hour. So that's going to be 3600 segments or seconds. And this will be the length of the bar, 50 meters. And so using the Crank-Nicolson method, we're going to start up by setting up equations for the average of the previous and the following temperatures. And so we can write here that we know that the change in temperature, or the change in time, is related to the thermal diffusivity, alpha. This is thermal diffusivity. And this thermal diffusivity is related to the rate of change in temperature of the bar. And that's related to the second derivative of the temperature over 2 position squared. And so we can write this in terms of the previous and following temperatures. Tj n plus 1 minus Tj n. And that's still over delta t. And that'll equal the same thing, alpha over 2 delta x squared in this case. And here, for the second derivative of the temperature, we'll have Tj plus 1 to the n minus 2 Tj to the n plus Tj minus 1 to the n, all over Tj plus 1 to the n plus 1 minus 2 Tj to the n plus 1 plus Tj minus 1 to the n plus 1. And so to simplify, we're going to be multiplying each side by delta t. But before we do that, we want to recognize that the r value given in lecture, we've gone over the r value, and that's delta t alpha over 2 change in x squared. And so here we see that we have alpha over 2 delta x squared. We're going to be multiplying the delta t, which is all going to be equal to r. And so to simplify and rewrite this, we will have t j n plus 1 minus t j to the n equals r times everything we had before. And I will just move that over to save some time. Okay, we can further rearrange this. We can further rearrange this by writing negative r tj minus 1 to the n plus 1 plus 1 plus 2r tj to the n plus 1 minus r tj plus 1 to the n plus 1. And that'll all equal r tj minus 1 to the n plus 1 minus 2r tj to the n plus r tj plus 1 to the n. And the left side is unknown while the right side we know it's either initial or 0. So we can break these down we can break down the matrices up. First we'll have right here, we'll have the coefficients. That'll go from j equals 0 to j equals 1, all the way down to j equals 49. And we know here at j equals 0, first line we'll have is negative r, and have 1 plus 2r, negative r to 0. And we know the trend is diagonally downward, and here at j equals 49, at j equals 49, we know we're going to have 1 plus r as the coefficient. And so the second matrix is just going to be for tj to the n plus 1. You know it's going to go down to t1 n plus 1. It'll keep going down to t49 n plus 1 at j equals 49. And that'll equal the last matrix right here, starting off at j equals 0 again to j equals 1, all the way down to j equals 49. We're going to have here our temperature, the left boundary, n, plus 1 minus 2r tj to the n, plus tj plus 1 to the n, plus, I'll write an arrow here, sorry for running out of space, rt left boundary to the n. And then for j equals 1, we're going to have r tj minus 1 to the n plus 1 minus 2r tj to the n plus r t, sorry about that, tj plus 1 to the n. And that is going to continue downwards until we hit j equals 49. For j equals 49, we're going to have r tj minus 1 to the n plus 1 minus 2r tj to the n plus r tj plus 1 to the n plus r tj plus 1 to the n. And here we actually do not have an r right there. And to further simplify this, at j equals 49, we're going to have r tj minus 1 to the n plus tj to the n, and we'll finally arrive at tj to the n equals tj plus 1 to the n.